Thank you. Welcome back to a new lecture from Hands-on Computer Vision. Today we'll be covering YOLO for the second time. In the last lecture, we discussed the theoretical aspects of YOLO, especially the YOLO version 1. Today, what I want to do is walk you through building an actual very useful YOLO project, which is for number plate recognition. So if there are vehicles passing in a video, it could be a live video stream, it could be a recorded video. Is there a way we can recognize the number plate of this vehicle and actually read it and convert it into a digital format? This will be useful in many cases. You know that there are AI cameras installed throughout the highways that can detect whether the passenger is wearing a seat belt, whether some other speed limit is crossed, etc. Those are AI cameras equipped with various real-time processing modules. We are not sure what exactly is the module that they use, but what we are going to do today is show that YOLO can be one of such real-time detection modules. So apart from YOLO, we'll also be using one more technology today called OCR, also known as optical character recognition. So YOLO will help us extract those pixels which forms a bounding box inside a bounding box for the number plate, and OCR will help us read what exactly are those digits inside the bounding box. So all of us will be building this together. So what we are going to be using is, for the first part of the code, we will be using Google Colab. For the second part of the code, we will be using VS Code. All right. So the basic idea of a number plate recognition system is something like this. Consider an input video. The video is divided into frames. There are around 30 frames per second. And what we want is, this bounding box is a little bit offset, but basically we want a bounding box around the object. And the object of interest is obviously number plate. And once that bounding box is obtained, meaning once the pixels of interest is obtained, the final output that we really want is the actual number plate number, right? Whatever that is, GX15OGJ, whatever it is. So this is the final output that we require, and this is the input. So the architecture that we are going to follow today is, first, we will use a YOLO pre-trained model. So pre-trained model is available. We have been using the YOLO V8 Nano version of the pre-trained model in the previous lectures. So we'll be using the same model, but we'll be doing one additional thing, which is fine-tuning this on the license plate dataset. I'll tell you exactly why this fine-tuning is needed in a moment. And then once we have a fine-tuned model, we will save the model so that the weights of those models are accessible to us. So we'll be training the model not from scratch. It is, you can call it as transfer learning. So it's a pre-trained model, you're fine-tuning on top of it. You can do the same for, let's say, GPT. If someone has already built a model, and if you want to fine-tune it on top of it, you're not starting with random weights. You are starting with very well-defined weights of the model, and then you are slightly modifying it. And finally, we'll be using OCR. But while using OCR, we have to add some specific constraints. This specific constraint will depend on the kind of data set that we have. The video that I'm going to be showcasing you today will have a specific constraint. Maybe the video that you are going to use for your application may have some other constraints. All right. So the reason why fine-tuning is needed is because the pre-trained version of YOLO that we have available from Ultralytics is the company that has many pre-trained YOLO models available for use. If you go to their products here, you can see the list of YOLO models that they have. They have everything starting from, I think, YOLO V1 all the way till YOLO V12. So YOLO V11. So here you can see all their models up to YOLO V12, but we'll be sticking with YOLO V8. It's very simple to download, and it's very simple to use. But you could also use YOLO V11, no problem. Now, the issue is that this pre-trained YOLO V8 model is trained on COCO dataset. This dataset has 80 object classes, and these are the object classes. I have just put the object classes into a word cloud. But the idea is that these object classes does not contain the class called number plate. So it's not possible for the original pre-trained YOLO V8 model to detect number plates, but it can detect all these things. So if our image contained any of these things, it could have detected the object, but not number plate. So this is the reason why we have to pre-train the YOLO model. And after pre-training, we perform fine tuning. So what do we need for fine tuning? Let me not show you the screen for a moment. Can you put in the chat, what all things do we need if we want to fine tune an existing model? What kind of data set do we need in this context? Okay, in the context of this problem, what is the data set that we need for fine tuning? Right, label data. And how will it look like? How will this label data look like? What will be the image, and how would the label look like? Basically, it will be photos or images of number plates, and the label is nothing but the bounding box coordinates, correct? Bounding box center, bounding box width, and height. And if we have this data, we can call it as a label data, and that we can use to train the existing YOLO model. So basically, to get the label data, we can use a platform called RoboFlow, where there is abundant data set available. So after fine tuning, we will get a model and we have to save that model weights. Only then we can use it later for inferencing, right? So I'll also show you how to save the fine tuned model so that you can use it any number of times. And the reason why I'm using GPU for the first part, which is the fine tuning part, is because fine tuning is a little bit slow. So if we have Google Colab, we can use GPU. So let's use Google Colab for the first part. And then for the second part, we can run on VS Code on our own computer. So even if you don't have GPU for inferencing, that's fine. But for fine tuning, GPU will accelerate things really fast. So this is the fine tuning step. And the data set that we have, annotated data set, is available on RoboFlow. So you can just go type RoboFlow and type license plate dataset, and then you will get this link. So I'll share this link directly in the chat. So just open this link. All right. So this is the data set that we will be using. And what you can do is go to this section called dataset. And in that, at the top, you will have different versions. I mean, on the left side, you will have different versions. We'll use the latest version. And we are going to download this dataset, which will be in a very specific format. So what you can do is select YOLO V8. So obviously, needless to say, you will have to sign in using your Google account or GitHub on RoboFlow. So click YOLO V8, and then you are not training from a portion, you are downloading the dataset. So select download dataset, then click continue. And what you can do is, instead of downloading the zip file to your computer, so don't select the download zip to computer option, just select show download code option, click continue. And then RoboFlow will display a code. You see this code, pip install RoboFlow, from RoboFlow import this. So just find the code and copy it. I'm not going to share the code with you because it has my API key, which I will destroy anyway later. But you can use the code that you get from your account. Once you have this code, you can go to Google Colab, open a new notebook, then paste the code somewhere in the first cell. And the pip install alone, you can maybe run separately, because that you don't have to run all the time. So this you can just initially run separately. This will install RoboFlow library, and we will need it. I have already installed it, so this will happen for me pretty fast, I guess. But for you, it may take 1 minute or something. And name it as something, YOLO plus OCR for license plate detection. All right, so this is done. And then here you can see some things. This is the API key, which will not work once I delete this, but you can use your own API key. then project version YOLO V8, RoboFlow Universe projects, and the project name is this. So it's all automatically filled, the project name and everything, and I can just run this. So when I run this, it will download the dataset. And where is it downloaded? It will be downloaded to this temporary folder here, over here. So this is a temporary folder. The moment you disconnect your runtime and the moment, I don't think this will go away when you refresh, but if the runtime gets disconnected, it will be gone. So just be careful with respect to this. So, but the downloading is done. It's very fast. Now, how does the dataset look like? We can just open this and see there are these three folders: test, train, and valid. In fact, yesterday I had downloaded it, so I can just show you how it looks like. So this is the dataset folder. So it has a .yaml file, which we will need. Then README is just we won't be using it. Then there is test, train, and valid. What do you think there will be in the, let's say, train folder? If I open this, what do you expect to see inside the train folder? Any machine learning problem? So Jayadeep has mentioned images. Are images enough, or something else is also needed? Images and labels, right? Labels, because we need to know the bounding box. So if you open this train, there are images, labels. This you can ignore. You won't be needing this. Now, in this images, there are a bunch of images of cars. It's not just images of number plates. So that's one interesting thing you should note. So these are just images of cars, okay? But some of them are images of number plates. So this is just an image of a number plate, okay? But it's a very nice data set. It has some cars do not even have the number plates. So see this. So it's a very nice data set. So this is how images look like, and labels look like this. If I open this, I hope you can see these numbers, although the font size is a little bit small. You can see there are like 4 numbers, or rather 1, 2, 3, 4, 5 numbers. Can anyone tell me what are these 5 numbers? And there are 2 rows. So what does it mean to have these 5 numbers in 1 row? What does it mean to have 2 rows here? This we had discussed in the last class when we were talking about the way final output looks like in YOLO. So one is class, X coordinate, Y coordinate, width, height. And since there are 2 rows, it means for this particular image, whatever image corresponds to this label, there are maybe 2 cars are there, which means there are 2 number plates, right? So that is what this means. But basically, but this won't be the case for all the images, because in most of the images, maybe there will be only 1 license plate, right? So here there is only 1 bounding box in this image. So every image won't have 2 bounding boxes. Depends on how many number plates are there. Okay. So basically what we did now is we downloaded the annotated data set from RoboFlow. Where did we download it? We downloaded it to this temporary folder within Google Colab. Yesterday I had downloaded it to my computer also. That's why I could show that to you. But these are those folders: test, train, valid, and then these txt files. And .yaml also you need. Then what we have to do is, so the structure of the data set, I hope this is pretty clear. Ignoring the txt file and ignoring the cache files, this is the folder structure, how it looks like. And as you guys mentioned, the first one is the class ID. The reason why class ID is 0 is because there is only 1 class here. There is only the number plate class. There is nothing else. So by default in this problem statement, we can assign class ID to be 0. Then this is the normalized center of rectangle, the X centroid, Y value of the centroid, width and height. I'm not 100% sure if this is the square root of width and square root of height. Maybe not. I think this is the actual width and actual height itself. This is kind of easy to verify. So Jaydeep has asked whether the 0 is class ID or confidence score. It's not the confidence score for this YOLO V8 annotation. It's simply the class ID. You will see that for every single file, the value is 0. It's not the confidence score. Okay. Now, what we should do is let's do the fine tuning. So you imported the dataset from RoboFlow, and then next is installing Ultralytics on collab. So just run this code, pip install Ultralytics. So I'll also do along with you. And before that, let me make sure that my runtime is A100 GPU. So if you don't have access to A100, you can simply purchase very minimum number of credits. It'll be worth it. Just purchase $10 worth of credit or something. Your code will run much, much faster. So yesterday I had tried running both versions of the code with CPU on my computer and with GPU as well. And I could see that much A100 makes it much faster. Okay, so that is the runtime, and then pip install Ultralytics. So this I think I have already installed, so I don't think it'll be needed for me, but for you it'll be needed. Yeah, I think T4 would be sufficient for those of you who do not have the subscription to Collab Pro. But please don't use just CPU. Use whichever is available for you. If T4 is available, use that. Now we are importing two libraries. One is the YOLO library from Ultralytics. I mean YOLO from Ultralytics. Then shutils. So this is shell utilities. Shell utilities is used for modifying files and folders. Import OS is also done here. Then let's copy paste these two libraries. I mean these three libraries. I'll paste the code in the chat. So do one thing, put it in different blocks. Don't put all the code in the same block. It will make the code ugly and difficult to read. Just keep it in different blocks for cleanliness. All right. So from Ultralytics, import YOLO and then import shutil and OS. Now, the model that we are selecting is obviously YOLO V8 Nano pre-trained. So each of these terms deserves some attention. So YOLO V8 is the version 8 of YOLO. Nano is decided based on the number of size of the model. So there are certain parameters that says nano, small, medium. There are some 5 different versions, I think, or 6 different versions rather. So nano is the smallest one and the fastest one among the YOLO V8. .pt means pre-trained. Okay, so the model that we are importing is YOLO V8 Nano pre-trained. And this is the part where fine-tuning happens. So we are training the YOLO model and we are training it initially only for 5 epochs. The more this is, the better. But from the data, from the video that we will input during the inference, you will see that the actual bottleneck is not YOLO. The bottleneck is OCR. So you will see that. So initially I had tried 50 epochs. Then I realized that it's taking too much time. Then I reduced it to 5. And I'll also show you the mean average precision. It's decent. So 5 epochs should suffice. Then image size, batch size for training, number of workers, device equal to 0 for GPU. And then what we are doing is we will make a directory called save models. And then if it's existing, it will be there. But otherwise, a new directory will be created. And then we will be saving 2 models. One is license underscore plate underscore best dot pre-trained. Then license underscore plate underscore last dot pre-trained. So last is the last model that was trained. Here we are anyway only training 1 model. And the best is the model which had the best validation accuracy. For today's purpose, once we train and once we save this, we will be using this model. And I will show you how exactly to download it. So first, let's do one thing. Just copy paste this block of code. So I'm pasting it in the chat. So copy that and paste that in Colab to run the code. All right. So if you are running on GPU, these 5 epochs might run in maybe 2-3 minutes. Results data equal to dataset lot location. Okay. I'm just checking where are we supposed to define the data set. Data set we haven't defined anywhere outside, so maybe we'll have to write one line here. So I'm just asking Gemini. Yeah, there is one more question. What more is left to cover in the bootcamp post YOLO? So post YOLO, there is one more topic, which is RoboFlow. So RoboFlow is an amazing platform. So the next two lectures will be on building and deploying applications for various tasks in RoboFlow. Meanwhile, can somebody confirm if you guys are able to run the code until this point? Of course, there is a missing variable error, but this we can fix. The reason why this data set was not defined was because the previous cell, when I changed the runtime, the previous cell execution got cancelled. So it was already defined here. Also, once you're able to execute the code, just tell me how many epochs have finished so far. I'm just curious for somebody who is running this on T4 or something, how much time is it taking compared to A100? I'm just curious to know, like whether one epoch is finishing in 2 to 3 minutes or something or not. With GPU, even one epoch was taking me, I could not even finish one epoch even after half an hour. So it was extremely slow with CPU on my computer. Okay, so here the fine tuning has started. So you will see the epoch progress in a moment here. So yeah, so see, this is the first epoch, 5, 7, 8% has finished. So it takes time, right? As you can see here. What happens is, let this keep running. I will directly give you the, okay, one epoch to 2 minutes, which means if you are running 50 epochs, it will take 2 hours, right? Roughly. So what I'm going to do is, I'll just show you once this is finished, where exactly you will find the downloadable fine-tuned model. But meanwhile, what I'll do is I will share the file, the pre-trained file directly with you. So not pre-trained, the fine-tuned one directly with you. All right, so I have pasted my pre-trained model on the chat. Once you get it, just download it. And where you have to paste it is in the VS Code. We had created a folder in which we defined all the environment, the working environment, right? So in that folder, you paste it. So here, this is my folder. And here I have pasted this license plate best model, best.pt model. So once you receive the file, just paste it somewhere inside that parent folder. Now we can have a look at how the actual code looks like. Actual code as in the code for inferencing, because pre-training fine-tuning part was actually fine. It's easy. The code part is simple thanks to the way this is defined. And downloading you can do from here. Let me check if my epochs have finished. Yeah, my epochs have finished. So what you can do is, oh, it has not finished. It's the third epoch. But yeah, you can go to this Yeah, that folder also has not appeared yet. The folder name will be saved model. So new folder will appear once the fine tuning is finished. All right. So in the folder, you will see a file called license_plate_best.pt, and you will see the three dots. So just click on the three dots, then click download. Then it will download to your downloads folder, and then copy paste that into your working directory. So overall, the pipeline is, as I discussed in the beginning, extracting the license plate using YOLO, which will give us this guy, but it will still not give us the license plate number because YOLO can simply detect the object. YOLO cannot detect the text within the object. For that, we need the optical character recognition. In fact, OCR technology you will come across in many cases. If you upload a PDF document to ChatGPT, ChatGPT leverages OCR for reading the text inside that. So OCR is I would say, since natural language processing has took off, OCR is like a technology that all of us are knowingly or unknowingly using almost every single day. So we'll be using that only, optical character recognition, for reading this text from this image. All right. So firstly, what is OCR? There are two types of optical character recognition techniques. One is traditional OCR, which does not have anything to do with deep learning. And the second is obviously deep learning based techniques where tremendous amount of training has done. Can YOLO detect damages on vehicles? Only if it's fine tuned. By default, damaged vehicle is not a class. But if we train the YOLO, if we fine tune a pre-trained YOLO on appropriate data set, then of course it can detect. But by default, it's not a category. Only 80 objects are part of the YOLO's original COCODE 80 dataset category. All right. So in traditional OCR, basically we are using like feature extraction. So for feature extractions, you could use filters. You could use other mathematical algorithms. And then the extracted features, just like how you do in machine learning, not in deep learning, just like how you do in machine learning, you can pass it through any classifier. You can pass it through support vector machine, hidden Markov model, or k-nearest neighbors. So you can pass it through any classifier to classify the extracted text into one of the categories. So if the text is alphabets, there is alphabet from 0 to 9. I mean, alphabets means A to Z. Numbers mean 0 to 9. So it depends on what the nature of the text is. And some OCRs are also able to detect text from different languages, not just from English. So one of the most popular OCRs from traditional approach is Tesseract OCR. If I understand correctly, they were originally developed by HP or something. And then later Google took over and started maintaining Tesseract OCR. And there is a library, if I'm not wrong, the library name is PyTesseract, for easily bringing Tesseract OCR into Python. So we could have used this, of course. So I had tried using traditional OCR in the beginning, but what I noticed is that the accuracy is not that great. Maybe because my images are so blurred and noisy. Then the second approach is deep learning based OCR, where you train an OCR, train a neural network for detecting sequence of numbers from the input data. Of course, we won't be training it. We'll be using a pre-trained OCR model. So the pre-trained model that we are going to be using is called EasyOCR. So this is deep learning based. It's not a traditional OCR method, and it's maintained by this company called J.AI. I was just looking at their GitHub repo. It has good number of stars. So 28K stars is no joke. It's tremendous. And I also looked at their website, J.AI website. Looks like they are known as a very strong OCR company. We can basically use any OCR. I'm not really peculiar on any the OCR type as long as it works very well for our case. So somebody has mentioned about Mistral OCR. If we try that and if that ends up working better for our use case, of course, no problem, right? So, but for now, for this demonstration purpose, let's keep using EasyOCR. Now let's come to the actual code implementation. So actual code implementation as an implementation of the inference part. We already have the fine-tuned model. Now let's see how to deploy it. So first is importing library. So what I have done is I have written the code in blocks. So I'll walk you through the code block by block, and I'll try to explain it as much as possible. And okay, there is a question, how to evaluate between different OCR methods. There are certain benchmarks that people look at. So best OCR models. So there are different OCR benchmarks. So this leaderboard, I think I had looked at this leaderboard once. I don't know if it was this one or another leaderboard on Hugging Face, but basically there are certain benchmarks that these guys follow. I'll just share the link in the chat. But basically the score that you get as a result of evaluating the OCR method based on that benchmark is the final number that says how good or how bad the OCR is. Okay, so let me walk you through the code block by block and line by line. So first we are importing CV2, which is OpenCV. Then we are importing NumPy, YOLO from Ultralytics, EasyOCR. So here you will have to, if you haven't used this ever before, you will have to do pip install EasyOCR. Okay, so this, please do this. Then RE is regex. I'll show you why we need regex, regular expression. And default dictionary and deque is also needed for a very specific reason in this particular case. Like I'll tell you exactly the problem that I was facing and the reason why I had to import this library and do a certain thing. All right, so first let me share this block of code with you, and I would want you to go to Visual Studio Code and run this. So go to VS Code and open your working directory, and there itself you can create the Python file. So I'll create it here. Okay, so this is the importing. Then so my working directory is still the parent directory in which all these things are there. So I have like lecture 1, lecture 2, all these folders. I have all these code files and video. So that the parent directory is not the subdirectory called lecture 8. It is the directory in which lecture 8 is present. So to know what is your parent directory, all you need to do is like type pwd, present working directory. Okay, now mine is some other directory. So cd dot slash YOLO in practice. So cd dot slash. Okay, now I think I'm in the right present working directory. Okay, so just importing. Then what we do is we import the fine-tune model. So this is where we use the saved model. Earlier we had saved a model, right? And by the way, my execution of Google Colab has finished. So now I can show you how to download the saved model. So this is the model, and you can see the mean average precision. So 5 epochs have finished, and the mean average precision is 0.828, 0.92, 0.943, 0.945, 0.963. So it has increased and sort of saturated. We can run it further, but I would say this is good enough. Now, there is a new folder here that has been created called saved models. And inside the folder, I have this thing called license plate best.pt. .pt means pre-trained. So I can click these 3 dots, click download, and this will download it to the downloads folder, and then make sure that that thing is copy pasted into the working directory. So this is basically the pre-trained weights and biases of the model. Okay, nothing but the weights and biases. Now, this reader equal to EasyOCR.reader. Here we mention the language, and if GPU is there, we enable GPU. If it's there, we'll use GPU. Now, here is where I'm using my regex. So this is of a very specific format. So what I have noticed is in the video that I was using, so I will show the video which I had used for detection. So I hope, can you see this video? Is my screen visible? The video that I'm playing right now. Okay, so in this video, if you pause for a moment, if you notice the format of the number plate, you will see that it's like 2 alphabets followed by 2 numbers, and then again 3 alphabets. KH05, ZZK, something like that. So I wanted to enforce this. I mean, this of course won't work for all sorts of number plates. This will only work for this type of number plate. But alpha, alpha, numeric, numeric, then again alphabet, 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 right? This format. So here, regular expression is a dynamic expression against which we can compare any variable. So here the regular expression is the first two characters should be from A to Z. Second two characters should be from 0 to 9. The next three characters should be from A to Z. So this regular expression enforces, or we can use this to check whether the format of the number plate that is recognized is in that format, number alpha, alpha, number, alpha, alpha, alpha format, something like that. Now, there were a few problems that I encountered, mostly due to OCR. I did not have any issue with respect to YOLO because YOLO was recognizing the number plate bounding boxes really well, but I was facing issues with respect to accuracy of OCR. I haven't created a requirements.txt file yet, Jerry, but I can create it and share it. But for the moment, the only things that you will have to install if you have if you have followed the previous lectures, this time is you will have to install EasyOCR. You may have to install at Ultralytics. That's it, I think. I think the rest of the things most likely you should have. Okay, so now going back to the issues. So here are the issues that I faced while running my algorithm. First one is there are so many cars in the video. If you notice the video that I showed you, it's a little bit densely packed frames. So there are cars that are occluding other cars. There's like a bit of overlap. So because of this, in some frames, cars will be recognized. In some other frames, cars will not be recognized. And what happens as a result is, in some frames, we will have number plate detected. In some other frames, number plates are not properly detected. And that was one issue, okay? So frame, like sort of like flickering effect. This is one issue, but this is a YOLO specific issue. This one can be solved only by having a very good training data for YOLO. This cannot be solved by OCR. Now, there is another flickering effect that comes due to OCR, which is just focus on one of the cars, okay? Just focus on, let's say, maybe this car, this AP05. The number plate is visible, but as the car gets closer and closer and closer to camera, the number plate becomes more and more and more visible. But the fact that number plate exists, even in the frames before, means YOLO will pick up the number plate, even in the frames before. But because the visibility or the number of pixels that span the number plate is very less in this current frame, because of that, OCR will say that the number is some let's say QY032, something like that. So OCR will say random. It will not detect it correctly. It will give us a random alphanumeric output. Not random, I mean whatever it detects, not the correct one. Then in later frames, it will detect the correct number plate. Then in some other frame, if the lighting or some issue happens, then again, there will be a flickering effect. So basically what I noticed is that if I continuously play the video after annotating, the numbers will keep fluctuating. So I'll first show you the final output video that we are hoping to get, one of the examples. So this, I guess you can see, right? See what's happening here. There is a little bit of flickering. Not in every frames the number plates are being recognized. And also you can see that the numbers that OCR is reading is also flickering a little bit. It's not staying constant, right? So this is an issue. So then how do we know that what is the actual number? In some frames it's correct, but in some other frames it's not correct. So see here, NEG, but we know that this is NBG, but most of the things are correct. And look at this frame. It's reading it a bit wrong. Instead of KH05, this is LR05. So these are some of the issues with respect to OCR if the image is so pixelated. But flickering issue can be solved to some extent. What do you think we can do? Like logically, what do you guys think we can do to prevent this, number plate number flickering effect? So that by the time some frames have passed, I can say that, oh, the number of this car was this. What do you think I can do? a very simple logic. So Jaideep mentioned take the final read. The problem with the final read is that in the final frame, right, if some pixelation or whatever happened, if for some reason, if the reading was different from the actual number plate, then final read will not be correct, right? But maybe what is a better thing to do? The better thing to do is just note down the number plate readings for, let's say, 20 frames, so that only 1 second or something is passed, 20, 30 frames. And in those 20, 30 frames, whichever is the majority, most number of times appearing number, pick that. And then do this for a moving window of 30 frames at any given point of time. So like exactly as you mentioned, majority voting. So that is one way in which you can reduce the flickering effect. And for that only, I imported this library, default dictionary and DQ, so that I can create like a DQ where each time a new entry is added, the oldest item will be kicked out of it, right? So we can create a moving window through the frames. There was one more issue, which was due to lack of brightness. So I also had to do a little bit of pre-processing. So once I get the bounding box corresponding to the number plate, then increase the brightness and contrast a little bit. So basic pre-processing before passing it into OCR. All right. So that is what I have done. And then the remaining things are easy. Like here, the extra things which I have done is whatever bounding box is detected, I'm just displaying it in a zoomed in fashion here so that we can read. It's not by default. It's just something that I have done to make this appear better. And then whatever the OCR outputs as the number will be displayed up here above this zoomed in bounding box. Okay, so that's the only thing. One more thing which I tried is playing with confidence scores. We can say detect the number plates only when there is good confidence score, but that is the only, I mean, right now there are no false positives, like there are no bounding rectangles around regions that are not number plates. Sometimes that can be an issue depending on the input video. Now I'm going to give you the input video. I think I can paste this video in the chat. Yeah, so this is the input video that not this, sorry, I just pasted the output video. So the input is this. I just pasted it in the chat. You should get it in 1 or 2 minutes. So you can use that video, okay? So now, oh yeah, one more thing. If, let's say, I have a number plate that says AB 1, 2, then QOC. Okay, let's say this is my actual number plate, ground truth. And let's say my OCR prediction is A8 before enforcing my alphanumeric thing. A8 I to Q0 C. Then you know that this guy is supposed to be a number. You know that this guy is supposed to be an alphabet. You know that this guy is supposed to be an alphabet, right? You have that knowledge. So what you can do is you can take an educated guess thinking that this 8 might have been the representative, and in reality, this 8 would have been B. So if you recognize an 8 at a location where you are supposed to recognize an alphabet, you can say this is a B. If you recognize an I at a location where you are supposed to recognize a number, maybe you can say this is a 1, right? Similarly, if you recognize a 0 in a place where you're supposed to recognize O, then you can convert this 0 into O. So what I have done is I have created a set of, and here we can of course add more. If we recognize 0, it is mapped to O, 1 is mapped to I, 5 is mapped to S, and 8 is mapped to B. Only when the OCR recognizes a number instead of an alphabet. Now the reverse is also true. What if OCR recognizes an alphabet instead of a number? Then we have to map an O to a 0, I to 1, Z to 2, S to 5, then B to 8, and we can add more here to make it much more comprehensive. This is a very logical thing to do. This is a pure hand engineered logic. Then what we are doing is if I, so this OCR text is input in the form of an array. So let's say we have 1, 2, 3, 4, 5, 6, 7. There are 7 digits in the number plate, right? So digit 1, digit 2, digit 3, 4, 5, 6, 7. There are 7 items. Then this for loop will go through each of the items inside my OCR text. And if I is less than 2, or if I is greater than or equal to 4, then we have to do something. What is that? So what exactly is this part doing? Can you think? It's very easy answer. What are we doing here? If I is less than 2 and if I is greater than 4, then we have to check something and we have to do something. What is that? So if I is less than 2 and if I is greater than 4, it means I is equal to 2. I mean, I is not 2 or not 3, correct? So less than 2 means it should be alphabet. Greater than or equal to 4 also should be alphabet. Second and third should be number. So if it is an alphabet, then we have to check whether a number has come in the place of alphabet. So here, this mapping this mapping num to alpha, here you can see that if the character which we are currently looking at is a digit, if it's a number, and the character is part of one of these. So if it is a digit, and if it is either 0 or 1 or 5 or 8, then what we do is, if it is 0, we convert it into O. If it is 1, we convert to I. If it is 5, we convert to S. And that corrected number is appended to this empty array. So this empty array will build up 7 times because this array is being run 7 times. So this whatever is the corrected number is appended to this empty array. Now, if I is greater than or equal to 2 or less than 4, which means it's supposed to be a number. And what happens is, first you check if instead of a number, if it's an alphabet, right? So if ch dot is alpha is true, and ch is present in this list among one of these alphabets, if ch is present in, if the character ch is present as O or I or Z or S or B, so if ch is either one of this, you convert, if it is O, you convert it into 0. If it is I, you convert it into 1. You're converting it into the closest number, right? So this guy, this if condition will take care of the fact that some wrongly identified alphabets, some wrongly identified numbers should be converted to alphabets. Similarly, this guy will convert some wrongly identified alphabets to numbers. And then what we are doing is we are returning something. Okay, so here just look at what is being returned. Can anyone tell what is this return? Just an empty character. What is being returned is, let's say instead of recognizing an alphabet, we did recognize a number, but that number is not part of this. That number is not 0, not 1, not 5. So let's say this number, where is my number plate? Yeah. So let's say B, instead of B getting recognized as an 8, let's say B got recognized as a something like, let's say 4. Then we can't do anything. We cannot say that, we cannot say that if we identified a number plate to be A4 I2Q0C, we cannot say that this 4 maps back to B. It's confusing. So in such a case, we simply ignore the frame. So we simply say that we return a null character. So that is what's happening here. We are returning null character if we are having a character which is not part of this closely mapped set of alphabets and numbers. Then at the very end, this function is returning something. Can you think, what is this? What is this dot join? I mean, you have an empty character, dot join corrected. So what we are doing is, finally, what we want as the output is not a number plate that looks like A, B, 1, 5, Q, C, H. This is not what we want. We want something that looks like this, AB15QCH. So of course, whatever we have here needs to be joined together to make one single string. But this join function that cannot exist by itself. So that's why we add an empty character, and to that we do dot join corrected. So final output will look like something like this. Okay, but please note, if some characters were like this, let's say in the place of a alphabet, we recognized a number like 4, then that character will be empty. So here, then this guy would be empty. It will look like this, empty character. Then what would be the output if that is an empty character? The output will be A15QCH. And then you can easily say that this is an invalid output. How? The length of this is not 7, the length of this is 6. But we know that the number plates that we are looking at are of length 7. So this is how you can implement different conditions to make sure that your algorithm is much better than just the vanilla OCR. Then here I have added another function for recognizing just the plate region before we even do the OCR. So what we discussed just before now is OCR, but before even we do the OCR, we have to convert the recognized region into a usable format. So let's say we have a cropped region which corresponds to the number plate part alone, not the car, just the number plate. So if it is empty, we return nothing. But if it is not empty, we convert it into gray format. So as I mentioned in OpenCV, it's not RGB, it's BGR format. So that is why it's BGR to gray. And then we do some sort of thresholding. So this thresholding makes sure that it's the readability of that number plate is better. So we do a binary thresholding where numbers below a certain threshold are converted to black, numbers above a certain threshold are converted to white. And to find the threshold, you use something called as Otsu's thresholding. So it's like a thresholding algorithm. And then you resize the plate, whatever is the plate pixels, you resize it into double the size so that you can display it. So here you might have noticed in my output video, the number plate that is displayed here is twice the size of the actual number plate. This zoomed in thing. So in fact, this is not twice. I had zoomed in even further in this video, but before we pre-process using the OCR, you can increase the size. And while increasing the size, new pixels are created. So what should the values of those new pixels be? You will interpolate. So you will interpolate from the existing values using cubic interpolation. Cubic interpolation will ensure that the values are like smooth values, right? So basically you increase the size of the region that you captured. You also perform a Otsu's thresholding, binary thresholding. And then you pass it through OCR to detect the character. And one thing you do is you only allow these things to be recognized from the OCR, only alphabets and numericals. And if length of the OCR result is greater than 0, so the ideal result should be 7, then this is a potential candidate, right? The number plate is a potential candidate, then we need to check whether it's an actual candidate or not. So what we do here is candidate equal to correct plate format OCR underscore result of 0. So here what we are passing is the OCR underscore result is this guy, which is the result of OCR applied to the cropped number plate region. So this will be like that, just the subset of the pixels inside the entire image. We pass it to this function, corrected number plate format, which will ensure that if there are some close candidates, the new number will be flipped to alphabet or alphabet will be flipped to number. And then what you do is you try to pattern match. So here see the pattern matching, plate underscore pattern dot match of candidate. So here is where the regular expression is coming. So regex, look at the plate pattern. So plate pattern is a regex of the format 2 alphabets, 2 numbers, again 3 alphabets. So if our input is matching this, then you take it. If it is not matching, then you ignore it. So plate underscore pattern is what we are matching this against. So here plate underscore pattern dot match the current candidate. If this is true, then we return the candidate. Now the candidate can look something like AB12 BQY. There may be a mistake. This may not be the correct number plate. There may be mistakes, but at least it will be in the correct format. 2 alphabet, 2 numbers, and 3 alphabets. Okay. Then here is the number plate stabilization buffer, which I mentioned, which is the one which reduces flickering. So here what I have done is I have created a dictionary inside which there is a deque of length 10. So here we are looking at the last 10 predictions in that box. Last 10 predictions meaning basically for most cases, the last 10 frames. And what I'm doing is this algorithm, the final output will be for a given box. Let's say I have 10 frames, frame number 1, frame number 2, etc. up to frame number 10. And let's say out of these 10 frames, in 4 frames, the number plate was read to be AB1 to PQR. In the remaining frames, it was a bit random, QS34, BYC, etc. So it was a bit random. But in a majority, if we were to plot a histogram, this guy is the guy with the highest frequency in the last 10 frames. Then we will say that, oh, this is the target. So this will reduce the flickering. So even if in the current frame, even if so let's say the current frame is the 10th frame. So even if in the current frame, the reading is something different, it doesn't matter. You will not display something different because in the past 10 frames, this was the majority. So it's like a majority voting. I hope this logic is very clear to you. Then the rest of the things are very simple. Now we just need to find the video. So we input the video, vehicle_video.mp4. Output, we store it in this name. We can put whatever name. This is the capture equal to cv2.video capture of input video. What if this was 0? If input video was changed to 0, what happens? Then what will it capture? It will capture webcam, right? It will be basically the live recording. I mean, live streaming. Then 4cc is the video codec, getting the right codec so that later while writing, we can use it. So here we have 2 more things. One is the extracting the width of the video from the width of the frame from the capture, height of the frame from the capture, then codec. And here we are capturing the frames per second of the input video. Basically in the output video, we are following a certain codec, certain frames per second, certain width and certain height. And here is the confidence threshold. This we can play with 0.3, 0.4, but it shouldn't matter too much because our training data for the fine tuning was kind of good. So confidence threshold, even if you increase it, I don't think it should be a problem. You should still be able to recognize number plates very well. Recognize just the bounding box of number plates, not the OCR. So this has got nothing to do with OCR. This has got only to do with bounding box drawing. Now we do the frame by frame operation. This we have done many times in the open CV part, but I will still walk you through. So in every capture, so here this while loop ensures that until certain condition is satisfied, your algorithm will keep on running the inference. So if it's a live stream, as long as live stream is running, this while loop will continue. Otherwise, if it's a video, if it's a recorded video, it will run until the frames are finished. So as long as capture is there, you are reading it, and the red frame is in this return, red comma frame. Then results, basically results meaning you have passed this through YOLO model and it's captured. Results are now available from model of frame. So model of frame means you are passing into the YOLO model the frame. Verbose equal to false means you will not be printing random outputs from your YOLO model in the terminal. If you want it, you can just put verbose equal to false, true, but keep it just false. I don't think anyone wants to read anything in the terminal. Then in the results, what do we have? In the results, we have a bunch of boxes. So each frame will be passed through the model, and the model will give us bounding box in every single frame. In some frames, there will be no bounding box. In some frames, there will be multiple bounding box. So that is all stored in this result. Then we select it frame by frame. So in the current frame, which is R, so for R in results, we are looking at all the boxes. So boxes in the current frame are R dot boxes. Then inside the box, we are doing a certain things. So we have the confidence score So which is box.conf.cpu. So we are just converting it into a NumPy format, NumPy float format. And we check if our confidence score is less than the confidence threshold. This was set to be 0.3. If it is less than 0.3, basically what this means is if the model is not very sure, if it's only less than 30% confident that there is a number plate in the current bounding box, then we ignore the current bounding box. So we just continue the loop. Otherwise, if it is greater than 0.3, we continue with the rest of the lines. Now, these are the bounding box XY coordinates where we map it from box.xyxy. So we convert it into a number format. And then the plate is simply the frame, but only the subset of the frame between y1 to y2 and frame between x1 to x2. So if the frame is this, let's say y1 is this, y2 is this, and x1 is this, x2 is this. So you are looking at this part of the frame then. And this is the bounding box that bounds the number plate. And here text equal to recognize underscore plate of the plate crop. So recognize underscore plate is over here. This function recognize underscore plate. So here inside this function only we are using the OCR reader and everything. So by the end of this function, we will get a number plate reading like AB12 BQY format. Okay, so that is this recognize number plate. And then this box ID is where we track the particular box ID, and we see for this box ID for the last 10 frames or for the last 30 frames, what are the license plate numbers that was output by the model. And then we just pick the majority voting from that. So this get stable plate is basically the majority voting from for the current box, and that is stored here. And this stable text is what we are going to now display. So we draw a rectangle, and the rectangle is drawn inside the frame at these coordinates. And this is the color, this is the thickness, I guess. And then whatever region we have identified as so this entire part is simply whatever region is identified as the number plate is enlarged a little bit, and it will be displayed on top of the actual bounding box. And then the recognized text will be displayed on top of this somewhere here, like the 7 digits over here. So this logic, this I don't want to go through because it's too specific to the way of this display. And then once it is done, you save the frame. If you want to quit in between, you can press the Q button. So this is for that. And then you release the capture, release the output, and destroy all windows, right? So now let's implement this. The logic of the code is easy, although implementation part, I mean, getting the whole thing correct can take some time. So I guess I shared you the import part so far. Now here is the part where we import the fine-tuned model. So needless to say, fine-tuned model has to be there in your, this pre-trained model has to be there in your working directory. Otherwise, this will not work. Then define correct plate format. So paste this function. So I'll just share the first part with you in the chat. So copy paste that. Then this is the function definition for correcting alphabets to numericals and numericals to alphabets if there are close matches. Then plate recognition function, just pasting it. Then number stabilization function, it's like a 10 frame buffer. And then getting the video input and defining the video output and the confidence threshold. And then here, this while loop is I would say, the main guy who does all the work. Okay, so this while loop is a little bit longer. So I will share the final code directly with you instead of pasting it line by line. So let me do one thing. Just open that this code which I just shared with you. And when you run the code, so I'll just share it, save it in a different file. You see YOLO. And just let me know if you're able to run it or if you're facing any difficulty. I just want to show you 1 or 2 frames. Okay, NumPy is not available. Anyone else facing this NumPy issue? Just let me know. This was not occurring till now. I think I modified something in the code. We can ask the Copilot to check the error. So meanwhile, can you let me know if you have been able to get any output? So I have given you the video which I'm using. I've given you the pre-trained model, fine-tuned model, and I've also given you the full code. So please check that. And while this is running, I'm just figuring out what is my import issue. It says NumPy, this NumPy of image is not valid syntax. I'll figure it out. But meanwhile, like I just wanted to cover one more thing, and please let me know if you manage to find what's the issue. So I'll tell you what the issue I'm facing. I'm facing this NumPy in this line over here. Where is that? Where I convert my output into NumPy format, floating point format. In this line is most likely where I'm facing the issue. So just if you can let me know what is the fix, any of you, quick fix, we can just run the rest of the code. All right. So line number, I think line number will be different. I've shared the code, but depending on how your code is structured. One last thing which I wanted to cover in today's lecture is something that we discussed briefly in the previous lecture, different YOLO models. So we'll come back to the coding part after discussing about different YOLO models. So as we know, there are YOLO V1 all the way till V12. But if we truly think about what are the three revolutionary models which changed significantly, which changed things significantly, it's obviously YOLO V1 is the first one, and then the other two are YOLO V3 and V8. So I want to briefly discuss about V3 and V8 in a qualitative sense, not in a mathematical sense too much, because it's out of the scope of today's lecture. It will take at least 1.5 hours to just discuss YOLO V8 alone. But here is a table, okay? So YOLO V1, what they did was they showed that for the first time, you can simply use one forward pass for object detection. And they used a custom CNN, and they had convolution layers. I think the number of parameters, we had done a quick calculation last lecture, I think. but it was a very crude model. It divided the image into different grids, something that looks like this. And then there were a grid of like 7 by 7 number, so 49 total subsections of the image. And each grid cell was supposed to predict the bounding box. So bounding box coordinates in terms of center, x comma y, and square root of width and square root of height, confidence score, which is the objectness, and then class probability distribution. So this is how YOLO's version 1 was working, and this was the basic backbone of YOLO version 1, backbone CNN. By the time YOLO V2 was introduced, there were a concept called anchor boxes. If you have attended my RCNN lectures, you might remember anchor boxes. So anchor boxes idea was something like this. So you predefined set of anchor points, and for each point, you define set of boxes of different aspect ratio. So here in this example, there are 9 different boxes, 9 different rectangles for each anchor point. What this will do is, it will prevent the issue of aspect ratio problems in the YOLO version 1. So in YOLO version 1, if there were weird aspect ratios of objects, it was causing issue. Long aspect ratio, it was causing issue. But here, and there each, each cell was predicting 1 or 2 bounding boxes. But here, each anchor point is predicting 9 bounding boxes of different aspect ratios. And then what is done is, the predicted bounding box is modified slightly in aspect ratio and in height and width through regression, right? So this anchor point concept was also introduced in the RCNN, region CNN. So that was done in V2. So other than that, V2 was pretty much similar to V1. But then by the time when V3 came, they did 2 things. One is they used residual skip-like connections. This was very similar to ResNet. So ResNet also has skip connections, which minimizes vanishing gradient problem. And one more thing which they did was they started something called multi-scale predictions. I'll show you exactly what I mean by multi-scale predictions. So in YOLO V1, we had discussed that if there are small objects in the image, that is a problem, because let's say there is a crowd, and in the crowd, there are the head of 2 people in the same, or 3 people in the same grid cell. Then that's a problem, because YOLO cannot draw 3 rectangles inside 1 grid cell. So this caused an issue. So what YOLO V3 did was, they had grids of 3 different scales: small scale, medium scale, and large scale. So here, the 3 scales, what it accomplished is, small scale grid was of the size 13 by 13. So this can detect large objects, because 13 by 13 means the total image will be divided into 13. 26 by 26 grid means the size of each grid cell will be whatever is the image size divided by 26, and whatever is the image size divided by 26, the height and width. And 52 by 52 grids per image means it can really detect small objects, because each grid cell will be image size divided by 52, right? So this, and then there were 3 predictions: small scale prediction, medium scale prediction, and large scale prediction. And these 3 predictions were used in combination to predict separately objects of smaller size and objects of larger size. So if there was an image where you have a crowd, the people who are standing in front of the camera, closer to camera, is basically things that you can take care with larger grids. So that will be taken care of by this particular feature map, the feature map that you get from 13 by 13 grids. But the people who are standing far from the camera, they will occupy, each person will occupy smaller and smaller space, which means you need smaller grid cells. So that will be taken care of by this feature map. And here you can see some connections. These are the residual skip connections, which will prevent the vanishing gradient descent problem. So this was almost similar to ResNet. So these are the 2 main innovations brought by YOLO V3. And this is another image which shows I got these 2 images from internet only, not my own images. Credits to the original people who made it. But this is a better representation in my opinion, because it shows different blocks in a much better way. All right. So this was about YOLO v3. But by the time we reach YOLO v8, you will notice one more thing. So let's go back to that table. So look at the anchors. So in YOLO v1, there were no concept of anchors. In YOLO v2, all the way till v7, anchors were still present. Anchors are those dots, anchor points around which you draw the anchor boxes. But then in YOLO v8, they eliminated anchors again. So it was called as anchor-free detection. So in YOLO v8, the structure is a little bit more complex, but it might resemble something similar to UNet, which you studied in one of the earlier lectures. So YOLO v8 actually has three parts: a backbone, a neck, and a head. So backbone basically extract features. So features as in, so in UNet, if you remember, what we had was an architecture which looked like this. Left-hand side was encoder, right-hand side was decoder. Then this was the bottleneck. And the prediction happened over here. Input was here. So here it was spatially big. XY features were big, but Z-axis, the number of channels were less. But by the time you reach here, spatially it will be only like 32 by 32 pixels. But number of channels will be like 1024 or something. So here it was more abstract features. In these layers, you had more exact features. And then you had connections going directly from the level 1 of the encoder to level 1 for one of the decoder and so on. So this was the unit architecture. So here there were features at different levels being extracted and utilized at the final classification head for classification. Not just for classification, I mean for segmentation. Similarly, here feature extractor has different levels. So feature extractors in the earlier levels, shallow layers, detect finer details. In the deeper layers, they detect semantic meaning. Semantic meaning meaning you are overall looking at the image rather than saying exact. You are overall trying to identify, oh, this is a bike, rather than saying this is a bike and here is the bike. And then the neck combines the features that are extracted by the backbone into one single representation called feature pyramid network. And then this feature pyramid network is passed into the head, which makes the prediction. I know that I'm talking at very high level here simply because of time constraint, because I don't intend you to understand the entire structure of YOLO v8 in this 5 minutes, but I just want to give you a brief overview. So if you look at the YOLO v8 architecture, this is the backbone, and this is the feature pyramid network. And then this is the head, the three parts of YOLO. And these heads are called decoupled head. They perform different things. So YOLO v8 also had another thing that it could do object detection, instance segmentation, pose estimation, like the key points if a human is standing, and also the routine image classification. So YOLO v8 was a very, very efficient model. All right. So V11, I mean, V9, V10, V11, etc. are all modifications made from, I would say, the significant changes introduced during YOLO v8. So one of the reasons why we have been keeping on using YOLO v8 model is because of its ease of using, but also because it was a very important model in the history of YOLO. There is a question if there is an efficient way to learn YOLO's evolution in depth apart from reading papers. I have looked at YouTube for some videos, but I haven't managed to find any. Blogs, I haven't found that many useful blogs, but I have found good review papers. Just one paper, instead of reading multiple papers, just find one good review paper that mentions the evolution of YOLO. Maybe what you can do is, feed the paper into this notebook LM, and notebook LM might convert it into this podcast format. And I have actually done that while learning quantum computing. What I did was I read a lot and collected all the things that I read into different PDFs, and I uploaded it into a notebook LM, and then it converted it into like a 90-minute or something, very long podcast. And then while I was walking, I was just listening to that podcast. So it was very nice. And the way they convert it is like a conversation between two people. You can pick the nature of like male, female, what type of voice. They have so many features. So just check this out. I really like this tool, especially for complex topics that take time to understand. So what you could do, Jaydeep, is find any good review paper if you don't like to sit down and read it entirely, which can take a lot of time and it can get boring, convert it into some podcast format and listen while you're walking. I think the speaking style and the kind of questions that Notebook LM creates for that, AI generated podcast is actually very good. One of the highest quality AI products that I have used. In fact, the three products that I really like so much is, one is Whisper AI. Whisper Flow. Second is Lovable, obviously. Third is Notebook LM. So three amazing proper use cases of AI wrappers. Now let's get back to the code and figure out what is going on. I really want to figure out. I would really appreciate it if any of you can help me with this. What is this NumPy error? Maybe I can also ask GPT, or I can ask here itself. Oh, it's working for me. So this, without changing anything, it's working. All right. Okay, maybe I just need to downgrade NumPy. Yeah, I remember this. Yeah, for OpenCV, correct. I remember doing this, but recently I had upgraded the version. Basically, the issue is that for OpenCV, you want a lower version of NumPy. So this we had done in the initial lecture, and yeah, thanks for the suggestion. So I installed a lower version of NumPy. I hope this will work now. Yes. So one of the things which I mentioned is Notebook LM. Another is Whisper Flow, WISPR for converting speech to text very easily for your daily use. Third one is obviously Lovable for making websites. So Whisper Flow is amazing. I'm currently using it. I can show you how to, one of the ways to use it. So let's say I want to type something here as a note, right? So all I can do is, so I'll say something. Welcome to Computer Vision Bootcamp. In this lecture, what we did was we looked at YOLO V8 for detecting number plate, and then we used Open OCR, EasyOCR for detecting the number plate characters. So then I just release my button and then it converts whatever I mentioned. I mean, depending on my clarity of speech, it will detect. So here YOLO is detected as YORO, maybe because of my way of announcing. But overall, I have noticed that it is very good. So I just press my function key. I use Mac. So I press my function key and it opens Whisper Flow. And then it will convert my speech. And when I release the function key, so this little notch you see under my screen is the Whisper Flows icon. And this is the Whisper Flow app icon, this W black color thing. So it's very good. I have even subscribed to it because I have exceeded their free limit. But our code is running very nicely, as you can see here. It's detecting the number plate, although there are some issues, as you can see. Sometimes they are overlapping, and sometimes two rectangles are being detected. So there are bunch of issues. This is not a perfect code, but you can imagine making this even more perfect by considering a lot of edge cases. So the stock video for this I found from pexels.com, but I really struggle to find good stock videos for testing the algorithm, because on YouTube, whatever I can find are already annotated videos. I'm sure something exists on RoboFlow. Maybe I should check. But what I encourage you to do is like try the similar algorithm that I gave you on different videos and see if you are facing similar problems or if the problems vanish. Because in this video, you can see that there is a lot of occlusion happening. A lot of cars are there in front and back. But in videos, something like this, so here I was implementing another car counting algorithm. Here, cars are a bit more sparsely spaced, right? But this was a different code. I'll share the code file with all you pro guys. But basically, different depending on the video type, the algorithm may work better, right? So please try that and let me know how you experienced it. But I think this is a good point to wind up today's lecture. We will meet again next Monday. Next coming Thursday for RoboFlow first part, and then the second part will be Monday. And with that, we'll wind up the bootcamp. So RoboFlow is a platform. I want you to install a few things before the lecture, which I will let you guys know on Discord before the lecture itself. So meanwhile, if there are any discussions or questions, please let me know in the chat. Can you share the code for YOLO training? Yes. So YOLO training, I forgot to share the code, I guess. Yeah, I have just pasted the code in the chat, so you can use that. So just to summarize our pipeline, right? We first get the YOLO pre-trained model. We realize that it's not good because it has not been trained on number plates. Then we fine tune it on existing labeled annotated data, and then fine tune model we download. Then downloaded model we use for inferencing. In the inferencing, YOLO is not giving us too many issues, but OCR is giving us a lot of issues. So one thing that I wish you guys can try is try different OCRs. See which one, if Mistral OCR is really good, try that. If it works really well, because if I can read as a human, I don't see why an OCR cannot work really well, right? But maybe because the one that EasyOCR is not very well trained, who knows? We can try different OCRs with better performance benchmarks and make the performance better. Right now, I'm not very happy with the output. I'm just okay. I'm partially happy, but I can read this. I can make out what is there on the number plate. So then I'm just a bit frustrated why OCR is not working, right? So if any of you guys can figure out, just let me know. But thank you so much. We'll meet again in a couple of days. Take care until then, and bye.